Oop, starting lecture late. If you're not here, do that first one. We're working on the second one. Like at the rawest level, you could just do this. But I just wanted to see if you remembered how that thing worked more than anything. Nothing wrong with literally just going through here and putting that. That's true. You may not know what that means, but it's still right. I know what it means. Oh, it's not right. Because that should be a +2. So the next one, when n is 2, I've got 2 plus 2 factorial over 2 times 2 minus 1 factorial. And then the third one, b sub 3 equals 3 plus 2 factorial over 2 times 3 minus 1 factorial. That's totally right, but it's not super informative. So what I would recommend is breaking these down and simplifying if we can. That's 3 factorial over 1 factorial. And that is 4 factorial over 3 factorial. 5 factorial over 5 factorial. And what do we got here? What's 3? What is this one? Can somebody tell us, help us? What does that simplify to?
2 factorial times 1.
Yes, what is 3 factorial? Absolutely.
6.
6. That's it. Yeah, so both all those things are correct. Let's get to like whole numbers. Anybody not see how to get that and need me to talk about that? Because at some point you really need to understand these factorials. We're good? Okay, cool. Let's talk about this one. I can do this real easy. Notice that the top is 4 times 3 factorial over 3 factorial. So there's just some cool little things in here, some tricks of the trade that'll help us. Does that make sense, why that top line is true? If you understand what factorial is, then that does make sense, right? This is 4 times 3 times 2 times 1. This is 4 times 3 times 2 times 1. And then these cancel, and I just get a good old 4. Could have done that a bunch of different ways, but I'm just trying to show a little bit of tricks here, and that one's just good old 1. Looks like this sequence is going down, kind of, right? Looks like it's decreasing. Let's take a look at that. So here's b sub n, and here's n. And maybe I want to understand this thing. So when n is 1, I get a 6 out. When n is 2, thank you, I get a 4 out. When n is 3, I get a 1 out, so that just cuts down to a quarter of it. I wonder if this thing keeps going down. Hard to say. So it does have you plotted out more than one value?
Yeah.
I'm really curious. Ooh, can I take a look really quick?
Yeah.
So I want to show everybody how to do that.
It's a lot.
It does, but it kind of, ooh, wait, I'm confused. Oh, we got negative values. So I wouldn't use negative values for that, just really quick. You can in a way, but it gets kind of weird. So Abraham was plotting out this thing for all sorts of values, actually fractional n's, like all the n's in between, getting a really interesting plot. And then negative ones, I would just say for us in general, that if I have something factorial, let's just make sure to keep that thing in there, non-negative. There's ways to make negative values in there, but it's beyond like the scope of this class. It takes like a crazy integral definition and all sorts of nuttiness like that. So let's just do one more. When n is 4, what do I get? So when b sub 4 is going to be 6 factorial over, I had this feeling this might start growing at some point.
Should be like 7 factorial.
7 factorial, thank you. Yeah, 7 factorial. And what's a nice simplification to that? What's a slick way to do it? What's the bottom in terms of the top?
6 factorial times 7.
Yeah, just like that, right? So I cancel this comes out, and I get a nice old 1/7. I don't have to crank out all those giant values. So this thing seems to be decreasing. So this sequence here never increases. It always decreases. We think so. We would have to prove this. There's actual, like right now, just looking at a couple cases of this, does not tell us that. Never increases, or so it would seem. Let's put that, or so it seems. To simplify this is actually an incredibly challenging thing if you wanted to understand it a little bit better. But that means this sequence has a nice name for it. So this sequence is monotonic. So monotonic means one direction, you can think of that. So moves in one direction. And that's either up or down. It's either always increasing or always decreasing, and with a little bit of a twist there. So this sequence is monotonic, and specifically monotonic decreasing. Wow, that is specifically monotonic decreasing. Monotonic. God, I'm having trouble spelling today. Decreasing. Let me give you a formal definition of that and the other. We could also have a monotonic increasing sequence. Today we're going to get some extra terminology and some ideas about sequences. That's really going to be the focus today. And then we're going to open up the web work and work on it together and practice using these things. So a monotonic increasing sequence. Here's an example of that. Let's say I had a sub n equals good old n. Here's a nice simple one. What does this sequence look like? A1 is 1, A2 is 2, A3 is 3. This sequence always goes up if you plotted it out. So the increasing, you have to plot it to really see it. That's what I mean. So increasing would look like this. This one's quite lovely. Just go straight up like that. Don't connect the dots because we're only interested in discrete values here. You can make a plot of these things, but you have to remember you're only sampling at those whole values. So here's the official definition. Officially, a sequence, a sub n. So notice this notation. I'm doing a bunch of different things today, kind of putting together what we had with pushing forward just a little bit. So a sequence, a sub n, notice this notation. You could also say or a sub n is monotonic. God damn it. Sorry, God. Sorry, people of God. Monotonic decreasing if a sub n plus 1 is less than or equal to a sub n for all n. Notice what this means. This means the next value is less than or equal to the previous value. So reading this might be a new thing for you, looking at these kind of subscripts. So what this means is a sub next is less than or equal to a sub current. That's a great way to look at that.
Why is it less than or equal?
Because we can potentially, as long as we don't go up. So monotonic decreasing allows actually to be constant sometimes. That's a great question. Monotonic decreasing of this, note, it just means we don't go up, but can stay constant. If I wanted to say that it always, never is constant and it always goes up, if I wanted to say this, that's strictly monotonically increasing. So that's monotonic decreasing. If we go down, and you can imagine what increasing is, I think, out of my thing. Can you write the definition of this out for me really quick, please? So, finish this up. A sequence, A sub n, is monotonic increasing if, what is the condition? What would be the condition for this? Everybody take a second, see if you can mimic that definition. I just want to give you practice with those subscripts, thinking about what is all going on here. Do you think you got it, Gabe? Or you got a question?
I think I got it.
Okay.
A sub n plus 1 is greater than or equal to a sub n.
What do we think of Gabe's hypothesis here? Looks good to me. Yeah. Basically, a sub next is greater than or equal to a sub current. And then I would just say here for all n, just to add a little bit of quantification. So again, this is a sub next, so it's less than or equal to a sub current. So this sequence here seems like it's monotonic decreasing. Let's take a look at another sequence.
Would it still count as monotonic decreasing if, like, let's say between 1 and 0 it went up?
Can you be a little more precise? Like
if, say, like at n of 1/2, if it's going ups at that point, would that still
oh,
be
that's an
monotonic?
interesting. I like that. So first off, we wouldn't use n equals 1/2 just right off the bat. So we would only use n as a whole number, usually starting at 0, 1, 2, 3. But that's a really awesome question. So let's take a look at what Abraham is asking. He's saying, what if I have a function that looks like this? Let's see, so it looks like you're going up, but if you were to plot the function, you saw maybe something like this. Probably, I think you're thinking of something like that, where in between the values, it's not behaving in a strictly up or down way. This would still be a monotonically increasing sequence. In fact, I could give you one, I think, like that. If you did something like this, I think that would look a lot like that. But I'm pretty sure it's actually just always increasing if we only worry about the whole values. Does that kind of help on that refinement? Yeah, beautiful. I've got one here in my notes that I'm trying to find. Ooh, let me ask you one. How about this sequence? What if I give you a sub n equals 1 plus 3 over n? And what I want you to do right now is answer, is this decreasing or increasing? And monotonically. That's the hidden secret word here, increasing. I'm going to give you 3 sequences. I wish I could show you how to do this in Excel, but I'm going to give you an app that I think might help with this as well. Put it up on World Class since you hopefully have your laptop with you today. Let's see here. I'm gonna have to get you that app a little bit later. But you could plug in some values to answer this question. You don't have to like rely on a computer. Good to not have to rely on a computer. You ever think you gotta give you're pondering?
Yeah.
You're thinking, cool, that's good. Where'd Scott go? Disappeared. Oh, there he is.
I was like, when that's gonna work? So they just said.
I gotta find some kind of app to plot with, for God's sakes. This might work.
It doesn't look like it's.
It does not. It does not look good. That looks better. Once I start pushing buttons on that thing and over here, everything usually gets really bad. Not good at all. You can probably find this app that I'm using once we get it up here too, and you see what you need to search on. Ah, there it is. Nice. That's a pretty good plotter. So the thing I'm using, I usually just go search, go to Google and I say plot sequences. And then that sound comes on and I'm plotting sequences. This camera seems a little fucked up. This is the worst. Now you know, oh my God, if I start doing this, hopefully I don't like have it crash down on Becky. So this is GeoGebra, GeoGebra, like zebra with a G.org, and they have this graph sequence plotter here. There's lots of other options. I would recommend Excel, but we didn't have a chance to do that. I'll have to get Excel in here with my laptop on Wednesday to show you how to do this stuff. So I'm gonna actually plot these out, and we can take a look together. Hopefully you've done a little bit of analysis on this. So that S sub n, that's just S sub n that we have there. So that is 1 plus 3 over n. And then I hit enter, and it doesn't work for some reason. Don't know why it doesn't work. Maybe it's starting at 0 and it barfed immediately. So let's
You
try
can
that.
you have to scroll up, it's at 0.8.
Oh, thank you. But I still should be seeing.
It worked for me when I.
Did it? Did it really? So the exact same app I'm using?
Yeah.
Wild. Okay, so let's see. Can I actually scroll down here? I didn't even think I could do that. Oh, thanks, Abraham. Oh, Abraham, you got the answers. Yeah, it's bigger than 1, isn't it? There we go. Is the sequence monotonic? Looks like it. Looks like it's always going down. Are we 100% sure of that? It's like looking at the picture, we're 100% sure of it. Let me show you how I can prove to you that that is going down. So if you were unsure if your sequence was monotonic, sometimes pictures are a little tricky and they lie to us. I'm going to take this expression here. So to show a sub n is, and I'm going to use this symbol from here on out, decreasing. Makes sense. Going down, I use an up arrow for going up. We can take the derivative and see if the derivative is negative. Right? Because derivatives tell you about increasing and decreasing based on slope. So I'm going to take d dn of 1 plus 3 over n. That's going to turn into negative 3 over n squared. This quantity is always negative when any n, except for 0. So notice that this is less than 0 when n equals 1, 2, 3. That means you're going down. That means you're always decreasing. Your slope of the curve that we would have if we filled in all the dots would always be downward. So this thing is definitely monotone decreasing. What about this one? What did we think about that one? Is that one decreasing, increasing?
Kind of does both.
Kind of does both, right? It's a little bit of oscillatory behavior here on this one. And that's coming from this negative 3 to the n. When you have a negative number to a power, it's going to create alternation, and it's probably never going to be either one of those things. Let's take a look at that one. So negative 3 to the n. And what in God's name did I just do?
I think that's what it's supposed to be.
Is it? Oh, because it's plotting stuff in between or something.
It's
That's-
because I think it's just going up and down really fast.
Yeah. It doesn't seem to be doing what it shouldn't be getting too high though. Oh, I guess it does get really high, doesn't it? Oh yeah, I guess it does. Let's take a look at this thing. I'm going to make a little table. So here's a table, d sub n. So I'm going to let n equal 1, and I've got 1 minus 3. Oh yeah, so negative 2. When n equals 2, yeah, that wasn't the sequence I really wanted, but it's okay. When n equals 2, I've got 1 plus 9/2. When n equals 3, I've got 1 minus 27/3. So let's see, this is like 1 plus 4.5. So 5.5. This is god awful. Negative 24/3. Oh,
Just negative 8.
Negative 8, yeah. Yeah, I got there the slow way. Yeah, because that's just 9. I'm going to do one more of these. 4 is 1 plus 81/4. 85/4. And that's like 20 something, right? Like 20.25 maybe, something like that. Sounds about right. So this thing is crazy. This thing is alternating back and forth, getting more extreme as we go along. This is not monotone. I'm going to recommend in general using an app like this on the web work to get a sense of what the answers are instead of just trying to, get out there and go at it on your own. What about this one? Both. This one is both. This is both monotone decreasing, because it's in that border case. Monotone increasing and monotone decreasing. Nice. I wish that middle one had been better than I wanted it to be, but it didn't turn out that way. Let's look at this sequence really quick. That's a nice sequence. You're utterly convinced that this will never be anything other than 1, right? There's no reason to believe that this could ever be anything other than 1. So this one here heads toward 1 as n goes to infinity. this one is equal to 1 all the time, so it never, the larger it moves, the further out it moves, it never moves away from 1. This one is never actually equal to 1, but the further out we get, the closer to 1 it gets. Let's look at that again. Notice where 1 is. It's right underneath this. In fact, this sequence here looks something like this. If you had 1 here, you would see the sequence getting closer and closer, closer to 1, never getting there, but getting closer and closer to 1. This sequence never gets closer to anything. So I want to talk next about what happens out when n is really large. So let me summarize here a little bit first. So a sequence a sub n gets closer to 1 the further out we get, the larger n gets. Sequence b sub n never settles down on anything. And sequence c sub n always is 1. It's a constant sequence. Ooh, before we actually get into this, I want to talk about b sub n really quick. Notice that in this sequence here, here's n equals 1. I can put a little horizontal bar across here, and the sequence lives inside of it. So there's a top that the sequence never goes above, and a bottom that the sequence never goes below. Same with this sequence right here. Just pick any little tube that moves horizontal and straddles 1. So like, here's 1. Here's the upper bound on this sequence. Sorry, let's go back to a sub n. I apologize, I'm being really spastic. So this is an upper bound. Things never go above that. Here's a lower bound. Notice there's a lot of upper bounds and lower bounds. If I pick any line above this one, it's an upper bound. If I pick any line below this one, it's a lower bound. In fact, what's the biggest lower bound for this one? What is the greatest lower bound? Think of all the horizontal lines I could draw underneath here. What's the highest one I could get that would still be under all the values of that top sequence? 1. Who said that? 1. Do you see how that would be 1? All right, cool. So these lower bounds aren't necessary. This lower bound isn't unique. The upper bound isn't necessarily unique. But that top sequence lives between a lower bound and an upper bound. So let's, before we get into this, note, sequence a sub n is bounded. That word is bounded, excuse me for my spelling, because we can find 2 values, a little m and a big M, such that the sequence is always between those 2 values. That's called a bounded sequence. Is C bounded? Is C sub n bounded? So look at this one here. This guy. Is this guy bounded? That guy's bounded, right? Is B, is the middle one bounded? That is not bounded. That one just keeps getting bigger and bigger. It oscillates to and fro. So A sub n is bounded. B sub n is not bounded. No matter what, B sub n's crazy. It's doing this. So no matter what you claim is the lower and upper bound, eventually you will exceed those. You just got to pick n large enough. B sub n is not bounded, C sub n is bounded. So two major things that I've talked about today, kind of spastically. The first one was monotone. What direction is the sequence heading? Is it choosing a direction and sticking with it, monotone increasing or monotone decreasing? This next idea is boundedness. Does the sequence live within a strip, a horizontal strip? The next idea is what happens as we move out to infinity. That's what this was when I kind of spastically got ahead of that. So for this sequence here, since a sub n can be made as close to 1 as we want by choosing n large enough, we say that the limit as n goes to infinity of a sub n equals 1. What this just means is, what is the behavior for large n? So what is the behavior for large n? That's what a limit's all about. What is happening when I'm way out to the right on that thing? What is the sequence approximately equal to? The b sub n sequence does not have a limit. It never settles down. So this limit as n goes to infinity of b sub n, does not exist. It never settles down. And then the c sub n that I had up there, the limit as n went to infinity of c sub n, that was just 1. Because it always was 1. C sub n equals 1. So that never changes. Let me give you a problem. Hold on, so what if I gave you this one? What if we had a sub n equals n plus 1 over n squared plus 2? Let me ask you a couple questions about this. First off, is this sequence bounded? BDD, is it bounded? You might want to plot this. I would maybe get out, if you have your laptop, hopefully you got a laptop with you. If not, get your phone out. Something. And you could probably bring this, just maybe on your phone, do a search on GeoGebra sequence, and you'll get this app. I think it should work on your phone. I'm pretty sure I've done that on my phone. Let's take a look. Let's see. GeoGebra. Maybe say sequence plotter. Yeah, that does it good. Yeah, that works pretty freaking good. It's really freaking tiny, but you can zoom in on it. Check it out. So tell me, bounded, the next question is monotone. Is it monotone increasing or monotone decreasing? And then the third question I have for you is, does it have a limit? Does it settle down on something as n gets bigger? I'll work on this with you then.
Do we have to say what it's bounded by, or just that it's bounded?
It would be, so like in the web work they won't ask you, but like in like real life, it would definitely be good to have a number for that, Sophie. Yeah, that's a great question. Especially if someone challenged you know, some rancorous soul. I got the plot out here. If you're having trouble getting the plot, I got it for you. you, Jaden, you were still writing that, right?
I'm good.
Were you writing what I just erased? Okay, good, okay, cool, okay, great. I'm gonna actually do this derivative real quick, because I'm curious if we can do this in a nice, rigorous way. Looks a little scary. I'm not sure. There we go. Okay, I feel good about that now. So what about bounded? Is this sequence bounded? Yes, beautiful. Can somebody give me an upper bound?
2/3.
Yeah, let's see, let's check it out. That's really pushing it there. You're getting tight on that, aren't you? Yeah, yeah. Is that actually 2/3 right there at the beginning? Is that the first sequence value?
Yeah, it should be 2/3.
Beautiful. So Abraham's going for this first value, absolutely an upper bound. All good. Everything would be below or at least that. So we could pick an upper bound equals 2/3. Is that the only right answer? How many right answers are there? Infinitely many. Any line above that is going to work. So this is the best. This is the best upper bound. What's the best lower bound?
Is it 0?
It sure is. It looks like it's hitting 0, but that's just because of the resolution of this. Check this out. This thing is always positive, right? When n is a positive number, that thing is always positive. So this is always above 0. So lower bound equals 0. Those are the best you can get. It's not the only right answer. Even any negative number would be a great lower bound. Is it monotone? Sophie, do you think it's so?
Monotone decreasing.
Monotone decreasing. Yes, it is. And I'm going to prove it. So it looks like it, right? You go to the picture always with the sequence. Get the picture first so you have an understanding of the sequence. Looking at this, it sure looks like it's going down, but how do I know it's not little oscillations in there that maybe I can't detect? So I took the derivative of this with respect to n. Used the quotient rule. Did a little bit of finagling and I got down to this. So check this out. Here's the derivative with respect to n. This bottom is always positive. The top, remember that n is bigger than or equal to 1 for us. So this is always at least 2. This adds more on. So this number right here is always bigger than 2. That means the top is always positive. And I pulled a negative out in front. So that's always negative, and we're always decreasing. So just giving some validity to what Sophie was suggesting over there. Yes, this is monotone decreasing. What is the limit? Does the limit exist? Yeah, Sophie, you're helping me out today.
Limit would be 0.
Limit would be 0. Does this make sense to everybody? How can I prove that? Let's take a look at that. You did some of this at one point in your life. So Sophie's claiming the limit equals 0. So what we'd have to do is investigate this right here. How would you do that? Somebody help me remember how to do this. What's the top going to? So n is going to infinity. What's the top doing? Going to infinity. What's the bottom doing? Yes, beautiful. So if you have one of these kind, what do you do with it? L'Hopital that sucker. So I'm going to L'Hopital it because it's an indeterminate form. So by L'Hopital's, this is limit. N goes to infinity of derivative of the top over the derivative of the bottom. Now we've seen this before. Top is fixed, bottom's blowing up.
It's on 0.
Going to 0. Exactly. So once you get to here, you've got a fixed over a blow up, you got a 0. Very nice. Very, very nice. I got one more to show you. Let's take a look at this one together. And then we'll take a look at the web work. Sine of n over n. Now you're definitely going to want to plot it, because it's got a trig function in it. Tell me, answer these 3 questions, please, for that sequence. Tell me, is it bounded? If so, give me bounds. Is it monotone? Does it have a limit? I won't plot it for you so you can have fun. I'm gonna plot it together. Let me make sure I've got enough. Yep. Oh, wait, say that again. Yeah. Did you plot it? Did you get a plot of it? No. Plot. Plot. Yeah, check it out. It's kind of interesting. There's a plot. That's a plot. You got a plot? Is that something? I don't think I want to see that. Let's get this sucker out. Oh, you got it. Okay. Ah, there we go. That's helpful. Unfortunately, you can't move this. Oh, you can. Yeah. Just fine. Oh, that's nice. Does this not answer all our questions? It doesn't prove our answers, but it answers our questions, right? Is the sequence bounded? Yeah, what's it bounded by?
Sine of 1 and sine of 5 over 5.
Ooh. Sine of 5 over 5 is sine, and that was this one here, that lowest value.
I think so.
That's pretty cool, Abraham. That's nice. I'm gonna go super cheesy here, and Abraham's giving like professional level answers. We don't need professional level to answer this. We could just say, notice that the top. So first off, let's just notice something here. The top is always less than or equal to 1, and the bottom is always greater than or equal to negative 1, right? So we know this. And I'm going to keep that up because that's actually going to help prove this thing right here. But that means that this top is always less than or equal to 1 because n is always bigger than 1, and this is always greater than or equal to -1. Because when n is 2, it's like -1/2. When n is 3, it's -1/3. It's moving that way. So this is bounded between -1 and 1 for crappy bounds. So bounded, yes. And I would say here, a sub n is between those two numbers for all n. I want to address what Abraham did though. So the best bounds, because that's what he gave us, the best bounds would be sine of 5/5 less than or equal to sine of 1/1. And did you use the graph, Abraham, to get that and kind of like work from there?
I looked at the graph and then I tried to calculate it a little bit with a calculator to see if it was that. I'm not quite sure on the 5/1, it's around 5.
Like, is it the 4 or the 5, right? That could be, okay, but we're gonna go with that. That's a hell of a good answer. Is it monotone? Should ain't monotone, right? It's oscillating like crazy. No, it is not monotone. What do we think the limit is? I heard it here. I hear like it's quiet. What do you think the limit is? What does it look like? Looks like a 0, doesn't it? Let me prove that to you. So the limit equals 0. We can use the fact that I wrote up there before. So to see this, we're going to notice this. Do you remember the squeeze theorem back in Calc 1? Boy, that was a long time ago. Sandwich theorem, maybe called it? No? Where does this go as n goes to infinity? Where does the 1/n go? 0. Where does -1/n go as n goes to infinity? 0. It goes to 0. Therefore, these two crush this one to 0 as n goes to infinity, and that's called the squeeze theorem. Or the sandwich theorem. Does that make sense? It kind of makes it really apparent, because it's what we're doing is we're just looking at the 1/n curve that is an envelope for the top. -1/n is an envelope for the bottom. And they both crush this thing down to 0. Alrighty, friends, so you've got a web work with problems you should be completely adept at doing right at this time. So I would like you to please work on that. The longest one is number 5. It's got a lot of parts. But let's start on this and talk about it while you're here. I'd like it to be, I think the due date's Wednesday.
let me shut this